Welcome to part 7 in our series of videos on the drying of fruits and vegetables. The topic we will be dealing with is the preparation of materials for drying. However, due to its length, it has been necessary to divide it into two parts, Part 7a and Part 7b. My name is Don Mercer, and I am with the Department of Food Science at the Ontario Agricultural College, University of Guelph. We will begin Part 7a with several acknowledgements and follow that with a brief introduction and a disclaimer. Then we will look at the selection of raw materials and basic preparation techniques. We'll end Part 7a with a discussion of peeling versus non-peeling. Then we will move on to Part 7b, where we will look at the pre-treatments of materials, which includes such things as blanching. We'll look at loading of the dryer and monitoring the dryer process. We'll look at testing for doneness and the storage of dried materials. And following this, we will wrap up with some summary comments. I would like to thank Mr. Andrew Goodwin, Associate Industrial Development Expert with the Agribusiness Development Branch of the United Nations Industrial Development Organization, for his considerable efforts in coordinating this project. I would also like to thank those who are assisting in the presentation of this material to various local groups. Their contributions to our training activities are greatly appreciated. The author assumes no responsibility or liability for any problems of any nature encountered through the application of the principles discussed here. This material is intended for instructional purposes only, and you need to be aware of the rules and regulations in effect in your country or region. We have now covered a variety of topics designed to provide background information in a number of areas relevant to food drying. We've looked at the reasons for drying, as well as the methods of drying, and then the drying mechanisms. We've moved on and examined the factors that influence drying and looked at safety and quality, which we followed up with a discussion of basic sanitation techniques. In this presentation, we will bring much of this together and consider how we need to prepare materials for drying to maximize the efficiency of the process. However, we also need to consider a number of aspects in addition to simply giving you instructions about cutting things up and putting them in a dryer. Please keep in mind that our concerns for safety and quality, plus the need for a high level of sanitation, are factors that play an important role in the preparation of materials for drying. In Part 5 of this series of videos, we examined safety and quality. Selection of the raw materials was an important segment of this. For the sake of brevity here, we will simply say that you must select the highest quality raw materials for any drying work that you do. Drying is not a process that can take borderline materials and magically convert them to high quality finished product. Remember, you cannot turn lead into gold. It's just not possible. The key factor to consider in the basic preparation of materials for drying is to do so in a way that will optimize the removal of water. You may recall from a previous presentation that drying is a process that occurs at the surface of the material and involves the movement of moisture from the interior portions outwards. Here's the diagram that we used previously to illustrate this point. We have the material represented by this orange rectangle, and on each surface we have a pool of moisture which actually saturates the surface with moisture. Then we can look at the center line of the material and consider the migration of moisture from the center out to the surface. So the diffusion of moisture goes from the center to the surface in an effort to keep the surface saturated. As heated air moves across the surface, we lose moisture in the process of evaporation. The first thing to consider is the basic shape and thickness that are most appropriate for your needs and for the material. Generally, thin, flat slices work best. They combine a relatively large surface area for moisture removal with a reasonably short distance for moisture to travel from the center to the surface. The thickness that you can use will depend upon the material itself. For materials that are easy to slice, such as mangoes, 0.5 centimeters or 5 millimeters is quite appropriate. You may want to go a little bit thicker, but not much. You do not want the dried material to be so thin that it breaks up into thin flakes when handled, but you also do not want it to be excessively thick either. So we can have it too thin, or we can have it too thick, but really what we want is to have it just right. Some materials, such as carrots, are very easy to dry in the form of slices, and they slice quite easily as well. There are tiny tubes or capillaries which run through the body of the carrot in order to carry water to the leaves as it grows. These tiny capillaries also aid in the removal of water in the drying process, and if you take a quick look at a carrot slice, you may see the tiny capillaries which look like small holes or tiny pores in the surface of the carrot slices. Let's take a look then at how carrots behave when they are dried in three basic forms. We'll look at thin slices or flat plates, thick chunks which may approximate spheres, and finally long pieces which are like cylinders. The results should demonstrate the effects of shape and thickness quite well. First of all, we'll look at carrots as thin slices, and these carrots have been cut to a thickness of 0.5 to 0.6 centimeters. The fresh carrots on the top show what they were like before the drying process, and the three slices on the bottom show the dried carrots at approximately 10% moisture. The dried slices were of high quality and they rehydrated very well in the lab. So what we did was we took the dried slices, which appear in the bottom of this photograph, and soaked them in boiling water for a short period of time and looked at them after they were rehydrated, and they formed a nice, plump, soft carrot slice which was quite similar to the original carrot slice. The drying time was approximately 10 hours at 50 degrees Celsius with an air velocity of 0.5 meters per second in the dryer. Then we moved on and tested 2.5 centimeter thick chunks of carrots with a 2.5 centimeter diameter. Here you can see two chunks of carrots in the top of this photograph, and in the bottom of the photograph you see what the carrot chunks were like after they had dried. The dried chunks were of lower quality than the slices and did not rehydrate well in lab tests. Drying was slow. It took approximately 28 hours, and that was done at 50 degrees Celsius and an air velocity of 0.5 meters per second once again. Capillary action did help a bit, but not an awful lot. Finally, we tested 10 centimeter long cylinders of carrot slices, and they had a diameter of 2.5 centimeters. In the top of the photograph, you can see the raw carrot before it was dried, and in the bottom, you can see what the cylinder looked like after it had dried down considerably. But the dried cylinders were of a very low quality, and drying was extremely slow. It took about 42 hours to dry these carrot cylinders, and that was done once again at a temperature of 50 degrees Celsius with the same air velocity of 0.5 meters per second as we used in the other tests. No rehydration tests were conducted on this material since we knew right away that it wasn't suitable for consumption. This configuration was totally unacceptable for drying, and mold growth occurred in numerous cases, as is shown in the photograph on the right. Let's compare the rate of drying of the 3 runs by using this graph. Once again, they were all done at 50 degrees Celsius with 0.5 meters per second as the velocity of air in the dryer. The first curve, which is the blue one, shows how the 10 centimeter long cylinders with the 2.5 centimeter diameter dried. And once again, it took about 42 hours of drying time to reach the desired low level. Please do not worry about the units on the vertical axis of this graph. Just compare the shape of the curves and how fast the moisture drops down to the bottom of the graph itself. Looking at the green curve, that's for the 2.5 centimeter thick chunks with the 2.5 centimeter diameter. And as mentioned before, it took about 28 hours for that to happen. Now the red curve is that for the 0.5 to 0.6 centimeter thick slices, and that took 10 hours of drying time. So I really think it's obvious from this graph that the 0.5 to 0.6 centimeter thick slices are the way to go for drying things like carrots, and it took the shortest period of time and gave us the highest quality finished material. Tomatoes have a very high water content. As mentioned previously, they can be as high as 95% water by weight. This really presents a challenge to us for drying. If you cut the tomatoes into flat slices, they will tend to fall apart in the dryer and lose their seeds and that liquidy portion which is called the placenta. So here we have a diagram representing a slice of this type of tomato which will perform poorly in the dryer. In addition, if you dry 100 kilograms of tomatoes with an initial moisture content of 95%, you will only get about 5.6 kilograms of dried product. You were advised to consider using Roma tomatoes rather than the larger, more juicy tomato varieties. Roma tomatoes tend to have a lower moisture content, which gives them a correspondingly high solids content. But you have to be careful here because some Roma tomatoes have been bred to have a high moisture content. Drying tomatoes with a higher solids content will lower the drying time and it will increase your yield per 100 kilograms of starting material. Roma tomatoes can easily be cut into wedges. Depending on the size of each tomato, you may want to cut them into 6 or 8 wedges. The wedges can then be placed with the skin down facing upwards in the dryer as shown in this photograph. The skin will serve as a means of containing the contents of the tomato while enough surface area will be exposed to the drying air to provide a satisfactory environment for moisture removal. When conducting training sessions on drying, the question often arises about whether fruits should be peeled or not peeled. This is particularly true with apples and to a lesser extent with mangoes, but it still needs to be considered. The first thing to consider is whether or not the peels will reduce the rate of water removal from the material. If the peel covers a significant amount of surface area, this is most likely going to be the case. So let's take a look at the material as represented by this beige rectangle. Normally, we would have moisture leaving the center of the material, going to the surface, and being lost or removed due to evaporation. However, if we have a peel on the top and bottom surface, this will block the moisture and prevent it from escaping from the surface. So we will not have efficient removal of moisture in this case. So the peel covering the surface can reduce the rate of moisture loss significantly. If the peel is just around the outside edge of the slice, and that would be the case with an apple ring, there will not be a significant slowing of the drying rate. This is because the majority of moisture loss is going to be from the top and bottom surfaces rather than from around the edges. The edges make up a small percentage of the total area available for moisture loss. And we can show that diagrammatically. So once again, we have this beige rectangle representing the material that's going to be dried, and we'll have the peel on each of the outer edges of it. Moisture, which would migrate from the center of the material to the surface and be lost by evaporation, can still follow that path. The peel that's covering the edges does not reduce the rate of moisture loss appreciably, so you can actually leave the peel on in the case of something like apple rings. There are those that argue the peels should remain on apples because they believe the peels have substantial nutrient content to them. So I've shown an apple here on the left that has not been peeled and the corresponding unpeeled apple ring. The apple on the right has been peeled, as has the apple ring that accompanies it. My personal preference is to peel the apples. This is because the dried peels become stiff and leathery. As a result, they annoyingly get caught in your teeth and may actually stick in your throat when eating the dried apple rings. Here's a photograph of an unpeeled dried apple ring, and you can compare that with the photograph of a peeled dried apple ring. And the one on the right is much more pleasant to eat than the one on the left. But once again, that's a personal preference, and you have to consider the preferences of the consumers in your marketplace. I would definitely recommend peeling mangoes. This will remove the problems of having a leathery skin on the dried slices, which reduces the final product to peel. And please don't get this confused with what we call case hardening. The skin in this case is the actual green skin or ripened skin of the mango, which is leathery in texture to begin with, and it forms an impervious layer to moisture removal that's even harder to chew once it's dry. So the skin may also reduce the rate of drying on the outside slices from each of the mangoes when you cut them apart, because that first slice from the outside of the mango has a tremendous amount of skin on it, and it's just not around the edges. It's over the entire back side of the mango slice itself. Now we will move on to part 7b,